Hey Curie Physics students, this is Mr. Crone, here to show you some of the demonstrations that normally I would share with students in class, but since we're here in the quarantine, I wanted to be able to demonstrate them for you. And part of the reason that I wanted to record them is so you could go back and see them again, just so you could see what really happened, and also because I'm going to ask you to talk about these demonstrations and be able to use the three laws to explain why what you saw actually happened. So I'm going to start with a couple close-up demonstrations. I'm going to pull you in a little bit closer so you can see better, and then I'll let you go back there and I'll show you some of the little bigger demonstrations. So I have a special device actually that's really made specifically to demonstrate the first law. And just to remind you, in simple terms, what the first law says is that if you don't exert a force on an object, that object will keep doing what it was doing. So I have a little post right here. It has a small cup on top of it. There's a clear plastic plate that sits on top of it that's going to prevent the ball from being able to go down into the little bowl. And it has a small hole drilled in the side of it, and really the only reason that's there is so that it will sit. And I can line him up directly over the hole. This is going to happen pretty quickly. I'll do it twice just so that you can see it. What my goal is to knock this plate out so quickly that it cannot exert any force on the ball, and as Newton would have said, since the ball was at rest and with no force acting on it, then the ball will stay at rest. Now that's only horizontally. Vertically, once the plate is gone, then of course the ball will accelerate because the forces will no longer be balanced. The downward force of gravity and the upward force from the plate, that's going to be broken so that only the downward force remains, and the ball will accelerate straight down into the cup. Watch closely. The plate's going to disappear pretty quickly. So try it one more time. All right, here we go. The goal in all of these demonstrations of objects at rest, remaining at rest, is speed. We got to get that plate out really quickly. Now this is a special device that's made by a company called Arbor Scientific, but most likely nobody wants to spend money to buy such a simple device. So let me show you the home version of the same demonstration. So I have a coin from, you guys can see that, from Haunted Trails. And I have this is actually from a notebook. I cut the back of it out, a little section. But an index card would probably be the best thing. You want something that is cardstock, so it's a little heavier paper. It'll kind of retain its shape a little bit. And I'm going to put something, I cut it so that it would be just big enough to cover the opening of the glass. And now I'm going to set the coin exactly in the middle. And again, the demonstration is the same thing. It's all about speed. You want to get this out as quickly as possible, because while it's still in contact with the coin, it will exert some force on it. So the quicker the better. The success of this really depends on you hitting directly sideways. And what I would do is hit a corner so that it spins. That's going to kind of stabilize its motion. It's going to get it out very quickly. And the quicker we can get it out, the better chances it's going to land in the cup instead of going flying off the table. So easy thing that you can do at home with just say a coffee mug, a little piece of your notebook cut out, and any kind of object that you can get to sit on top of it, you should be able to pull off that demonstration. Okay, I'm going to try one real quickly. I don't know if this is going to work or not. Sometimes I can make it work, sometimes I don't make it work so well. Set this up just a pinch. All right, I have an aluminum Coke bottle. This is from Japan. I don't know if you can see the writing on there. So aluminum Coke can, and I'm going to balance a ring on top of it. Okay, and then I'm going to put a nail on top of that facing upward. All right, let's back that up just a pinch so you can see a little bit better. Okay, the bottle, the ring, the nail. So the goal is to get the nail into the bottle without touching the nail or the bottle, and only touching the ring. Now, it turns out it's super difficult to do, and I'm probably going to fail. Almost certainly I'm going to fail. But if I can hit this directly sideways so that it does not exert any force on the bottle or on the nail, then I should be able to get it out quickly enough that the nail will break the balance between gravity and the ring pushing up, and it should fall straight down into the opening. I know gravity is working in the right direction. It's going to pull it straight towards the opening. All I need to make sure to do is not to exert any sideways force. So this is all about speed. See if I can pull this off. That was a miracle. I pulled it off on the first try. Okay, that's a little tougher one to pull off. So of course, it's a really good demonstration. Okay, so now before I show you this little guy, little toy that I got in Japan, let's show the one that everybody is most excited usually for, and that is we're going to pull a tablecloth out from underneath some, I wouldn't say expensive dishes, but they are my dishes, and I would prefer not to break them. So let's talk first about the sheet. So one thing you'll notice about this sheet is that the edges have been cut off. So they look frayed, and maybe that looks like that's not good, but actually what you don't want is if they've sewed it or they've rolled this thing over and put a stitch in here, then there's a little lip to the fabric. So I want the fabric to pull very smoothly through. You want to use some generally kind of man-made product like polyester or nylon. They tend to be a little more slippery, they'll slide off the table a little bit better, and then also the glassware will slide a little bit better. We're going to use the glass from the last demonstration, and we'll go a little bit nicer with the wine glass on there. So very lightweight, really got to pull quickly in order to get out of there so this guy doesn't flip over. Make sure the glass is clean. And we'll put the Tibetan bowl on there also. Okay, a couple things about the way you do this demonstration. So first of all, as I've told you, I've very carefully chosen the tablecloth that I want to use. You can see that it's not the full width, so I don't have to deal with the entire thing. I'm only going to have to deal with just this small portion that I have to pull out. Now, the trick is you really need to get this thing going fast, but it's almost impossible to do that. So what I'm going to do is I'm going to take some slack. I'm going to allow my hands to come up here. I have a lot of the fabric is hanging down here, and that way I'm going to start to move my hand slightly downward, not up, definitely not up. Up's going to flip them over. Either straight sideways or better yet, slightly downward. That's going to make the fabric pull very smoothly across the table. And by the time this thing becomes tight, my hand's going to be moving so fast, the tablecloth is just going to shoot right out from underneath there. Hopefully, fingers crossed. Let's see if I can actually pull it off. I'm going to take a little bit of the slack out. I really only need a little bit of space because one of the things I want to avoid is hitting my own leg. So I need a little bit of slack, but I also need to get myself out of the way. Here we go. 3, 2, 1. Most exciting demonstration in which nothing happens. I saw the bowl wobble just a little tiny bit, but that wasn't too bad of a demonstration. But remember, it's not going to work well the first time you do it. So you want to make sure to use some kind of plastic or something you're not going to be worried about when the thing breaks, which is a good chance that it'll take you a couple tries to really commit to pulling that thing as hard as you can possibly pull it to get it out from underneath there. Okay, let's get rid of these guys. Let's move on to this toy from Japan. So this toy is composed of little wooden rings that have a small hole in it. That's just basically so that they can hold the hammer that fits down inside of them. The goal with this thing is, of course, just like the last demonstrations, if I can hit this bottom one hard enough and put the hammer through before this guy falls down and hits the hammer, then what should happen is this guy will just continue to drop down and you'll see the blocks disappear one right after the other. So let me just knock one block out, and then we'll try to go for all of them. All right, we'll put the green one on the bottom. Put our gentleman here on the top. Okay, this is super difficult to do because you really have to commit to just basically hitting and swinging all the way through it, because not only do I need to knock the block out, but I have to get the hammer through also before the block falls. And you can see I only have about, from the top of the hammer, I probably only have about 3 or 4 millimeters. So you really have to hit this thing hard. You're ready? Oops, here, let's do this. There we go. Okay, so the way the toy is actually meant to be used is you're supposed to knock them all out at once. So essentially I'm going to go back and forth, and hopefully when I'm all done, his head will just be sitting on the table right there. This almost never works, just so you know. Full disclosure. This almost always fails. All right. Requires you to commit to going back and forth as quickly as you can. Here we go, 5 times back and forth. Oh, so close. Kind of got a little bit off track at the very end there. First couple came out pretty nicely, but those last ones, they were pretty sad. All right, well that's about as dynamic as you can get with the first law, where you keep objects at rest at rest. So let's talk about the other side of the first law, which really the first law says that objects maintain constant velocity when there is no force acting on them, or when there is no net force. That's really the way the first law should be thought of. When you think about objects at rest, that's just a special case where the velocity happens to be 0. It could be -5 or it could be 1,000,000. It just happens to be 0. 0 is just another speed, another velocity that an object can have. And what essentially Newton found was that there's nothing really special about that. That's not what's special. What's special is when objects accelerate. So what I have is this is the little hover ball. It does actually have little colored lights to make it a little more exciting. But essentially what it does is there's a small fan underneath here with a little opening that's drawing air through. It pushes the air out through the bottom, and since there's a little lip on there, it kind of catches the air a little bit, and it builds up a little air pressure underneath it, and that allows this thing to slide with virtually no friction. And while I know this is not going to be the most amazing demonstration, I think you can appreciate that if we had a very long hallway, and I turned this on and gave it just the tiniest little push, I would just watch that thing slowly move at the same speed forever until it ran into something at the other end of the hallway. Just to show you how easily it moves. So even just the slightest little touch, and it'll just continue to move off in that direction. There's so little friction in this object that essentially the only thing that could bring it to a stop is the drag force because of the air. Very, very low friction. If we were in the school, we'd take this down to the hallway, and we would push it down to watch this guy just slowly make his way all the way to the other end of the hallway with just the tiniest of pushes. But here is something from our storyline. So one of the main emphasis in our storyline is that we are looking at the safety of cars. And so we're looking at a lot at this point right now as we talk about forces as what kind of injuries do you sustain in a car and what causes those injuries to be sustained. And we want to think about how Newton's laws helps to describe what's happening. So we're going to imagine this is a little doll, right? I believe it's a dog or a monkey. And I have one of the lab carts. I'm going to sit this guy on here, and I have an 8-pound weight over here. And I'm going to take these two, and I'm going to give them a little bit of a push and have them run into this weight. And we're going to pay really close attention to what happens, and then we'll talk about how Newton's laws describes, yeah, that's exactly what Newton's law says should have happened in that situation. And then we can think about how that leads to injuries. What are the injuries? Where are they coming from? Why is it that you're sustaining those injuries? So let's leave the weight right here. I'm going to try to hold this guy in place so that he moves with the car. So when I let go, he will stay exactly in place with the car, and pay attention to what happens when he hits the weight. So hopefully it was pretty obvious that the car came to a stop almost not instantly, but very, very quickly. Where what happened with this guy, because there was nothing to act on him, because there were no forces acting on him in the horizontal direction, now there was a little bit of friction, there was a tiny bit of friction, and of course there's the lip right here at the front that he might have kind of caught on just a little bit. So it's not like the car didn't exert any force, but he exerted very little force. And as a result, he continued to move forward at the same speed in a straight line until something else brought him to a stop. Now you can imagine in a car, you don't have a lot of good options. If you don't come to a stop with the seat, you've got the steering wheel, the dash, the windshield. The things that you have that are going to bring you to a stop are not going to do it as nicely as that seatbelt would have brought you to a stop. So the goal with the seatbelt is that when the car comes to a stop, you come to a stop with it, with a device that's going to reduce the amount of force that you're going to feel. So I have a seatbelt on this. These are rubber bands. So we will seatbelt the little dog in. And now, much safer, Because at least, even though the dog's going to feel a good acceleration, at the very least they're coming to stop with the car, so that rather than the steering wheel or the dash bringing them to a stop, the seat belt, which is much, much gentler on them, is bringing them to a stop. So objects in motion remaining in motion, that's a lot of where the trauma comes from in car accidents, because without a seat belt or something to restrain you, you are going to continue to move forward until something else in the car stops you. What we want is to make sure it's always the seat belt that's bringing you to a stop. Okay, so that's the objects in motion remaining in motion. Let's just take a quick peek at the second law. It's a little, I don't know, I feel like almost unnecessary to demonstrate the second law, because I feel like that one was not difficult to understand. It's really the first law that's conceptually so hard to understand. But to demonstrate that, let's see. I seem to have lost my piece here. Well, that's fine. We'll use this one. I have a wiffle ball and I have a baseball. Okay, now let's watch them as they fall and see if they fall at the same rate. I hope that was pretty clear that that guy fell at the same rate. Okay, now the reason for that is something to think about. Why do they fall at the same rate when these guys are nothing alike? This one's hollow, very, very lightweight. This guy's solid, much, much heavier. So they fell at the same rate, but let's watch what happens when I apply the same force to them. So the wiffle ball is closer to you, the baseball is a little bit further. I'm going to use this box. I'm going to give the box a little push. It's going to apply the same force to each of these guys, and let's just see how they respond. 1, 2, 3. So the wiffle ball had a little bit more acceleration. Realize the acceleration just happened right at the very beginning. Right at the very beginning, they each got a little bit of a push, and that caused them to accelerate, but the wiffle ball won. And the reason he won is because he has less mass. So when the same force is applied to two objects, then whichever of those has less mass is going to accelerate more rapidly. Let's try it one more time here. There we go. 3, 2, 1. So big difference in the way they respond when they receive the same force, and that's exactly what the second law says should happen to those guys. Okay, so this demonstration that I'm going to show you right now is, I would say, essentially kind of like a partial demonstration, because I would really like to be able to drop this thing to show you what this scale is going to read when I drop the thing. Now, unfortunately, I don't really have the space to do it right now, so I'll do that in a separate video. I would also like to make sure that that video is in slow motion so that you can see really clearly. This is a Newton scale, so it measures the force, but it measures in newtons instead of pounds. And in my other hand, I have a 1 kilogram mass. Now, if you think about what the weight of 1 kilogram is, the formula for weight is mass times gravity. It's a force, so it's always m times a, but in that case, the value of gravity, which is 9.8. So just think about it. 1 kilogram times 9.8 is 9.8 newtons. And when I hang this guy on here, you'll see that this guy is exerting a force of around just a pinch less than 10 newtons. Just a tiny bit less than 10 newtons. Okay, so right now we're talking about the first law. Okay, I'm doing my best to not only not move, but again, most important thing is that I do not accelerate. So I'm going to have this thing move in the upward direction, but I'm going to drop it down just a little bit, and I'm going to move it at a nice steady speed and watch the reading on this guy as I pull this guy up. Moving it nice and steady, and I realize I'm moving very slowly, but it's not because I'm moving slowly, is not the problem. The reason why you don't see the reading changing is because I'm not accelerating. I'm trying to move slowly so you can see it more clearly. Now what I want to show is what happens to the reading on the scale when I do accelerate either in the upward direction or in the downward direction. Now realize we have two forces working against each other. One is weight, which is pulling that weight down, and the other is the scale, which is pulling up on the weight, preventing it from going down. And because the scale, it doesn't show you what the weight is. You might think that the scale measures your weight, but it doesn't. It measures how much force is being pulled down. Watch, I'll pull down on the weight. Did I make the weight heavier? No, I didn't make the weight heavier. I added another force to it that caused the scale to acknowledge that there's more force being exerted than just the weight. Now, what I want to demonstrate is what happens when I accelerate in the upward direction. Imagine you were in a ride at Great America that goes straight up, or perhaps on a really fast elevator like at the Willis Tower. Watch what direction the needle moves when I first begin to accelerate in the upward direction. And listen, I can only accelerate for just a split second. So it's that first movement you want to watch to see what happens when I accelerate up. Here we go. 3, 2, 1. I'll do it again. 3, 2, 1. You're looking at what direction did the needle go when I first moved the object upward. Now remember, it's not moving it upward, because if I move at a steady speed, then I won't find anything. What I need to do is to accelerate. And when I accelerate by giving it a quick pulse in the upward direction, you can see that the scale first went this way up to somewhere between maybe 12, 14, maybe even 16 if I pull quickly enough. And then I have to slow down. So what happens when that goes on is then the scale flips back to the other side. But now I'm back to rest. And so now the forces are balanced again. And so the upward force from the scale is just simply equal to the weight of the object. Now, what do you think is going to happen if we start to accelerate in the downward direction? When you're in a ride and the ride begins to accelerate downward quickly, like let's say a roller coaster or the big drop at Great America, then what you feel is very light. Your weight has not changed, but you feel lighter. You feel floaty. You feel like you're floating in your seat. You don't feel the seat anymore when the thing drops vertically, right? I mean, I'm sure that that's your experience. So watch what happens to the needle when I accelerate in the downward direction. You're looking for the first direction the needle moves. What direction does it move first? It goes to a lower force. Now, obviously, as I pointed out, I'm not changing the mass at all. I'm not even touching the mass. The mass is hanging from the end of the scale. But when I accelerate in the downward direction, you see the scale goes to a slightly lower reading. What do you think would happen if I dropped this scale? What would the reading go to? That's something to think about. Now, we'll do that as a separate demonstration so that we can all see it in really super slow motion. So you can see exactly what happens to the needle when the thing gets dropped. But as you can imagine, that has a huge impact on what this scale reads when I drop this. But the balance of the two forces, what determines what's going to happen, what the scale is going to read, is how I accelerate the mass. When I accelerate the mass in the upward direction, it requires the scale to exert more force. Because the scale has to exert the force that's equal to the weight, plus it needs a little bit of extra force to produce the acceleration. Just producing a force equal to the weight will keep everything the way it is. But if I want to make a change to it, I need to add or subtract some force. So if I accelerate in the upward direction, I get bigger forces. And if I accelerate in the downward direction, I get smaller forces. Okay, so that's the end of the second law, and we'll do one quick demonstration here for the third law. All right, we're going to move some stuff out of the way. And I'm going to point you guys at the floor. All right, so for this one, we're going to watch and we're going to talk about how the third law is really important. In fact, it would really be almost impossible to explain propulsion without the third law. The third law says that when you exert a force on one object, that object exerts a force back on you, but it's in the opposite direction. So if you think about when I walk forward like this, I'm standing at this piece of tape. I want to walk forward. I want to propel myself forward. With no other outside object, I'm going to propel myself forward. But here's the thing, I do need to have something to push against. And what we use when we walk or when we ride on a bicycle, a motorcycle, a car, or any other vehicle that has wheels, what we are using is the frictional force between our feet and the ground, or between the tires and the ground. So just think about this. If I want to go in this direction, I don't push that way. In fact, I can just imagine right now, if I push that way, what would happen to me? I would go backwards. So when I push forward, I feel myself pushing forward, it propels me backwards. When I want to go forward, what I need to do is to push in the opposite direction. I push backwards on the floor. The reason why I move forward is because I know the floor will return the force, but in the opposite direction, and that is what is propelling me forward. So when I walk in this direction, I push backwards, it propels me forward like this. Now what I want to do is to try and take away the friction. So probably going to kill myself doing this, so watch closely. Probably won't be able to do this too many times. I'm going to try and take the same step, but I'm going to do it from this skateboard. I'm going to line myself up so that I am close to the line. I got my toes pretty close to the line right there. And now, hopefully without killing myself, I'm going to take one step forward, and let's see how far I go. So you can see, I did not make it very far. It wasn't like the last time I took a step. The last time I took a step, my foot was way out here. This time when I was standing on the skateboard, what happened was I went to push backwards and I applied the force to the skateboard, but because the skateboard has very little friction in the wheels, the skateboard just moved backwards on me. And as a result, I didn't end up going anywhere. And that's how the third law really helps to explain propulsion. We always push in the opposite direction, and that's what propels us forward. And the most challenging thing to understand, of course, is the rocket. But that's something that I'm sure you will explore in class. The rocket is a very interesting idea. Boats push against the water, planes push against the air. We all push against the ground. Not only the ground, sometimes, like, let's imagine in soccer, for example. I'm sure if you're playing in soccer, you push off the other players. Why do you push off the other players? It's not just to be cheap. It's not just to try and be dirty and to mess with them. It's because it helps you to propel yourself in the direction you want to go. It's just a natural instinct that you know that if you want to really change your direction of motion very quickly, and all you're going to push against is the ground, well, the ground is limited in terms of what it can do. But if you had something else that you could also push against, like a person, it helps you to make that change in the direction of your motion. Because what you need is to propel yourself by pushing against somebody, and that extra person to push against just provides you that extra force to allow you to accelerate more rapidly in the direction that you want. When you grab onto their jersey, that's you being kind of cheap and dirty. But I will say this, when you grab onto them, then you suddenly feel a force that pulls you forward, and it helps you. It gives you a little extra force to help you keep up with them. So while it's probably kind of a cheap and dirty thing to do, certainly it makes sense if you're trying to stay up with that person, is to allow them to supply you with the force while at the same time you're applying a backwards force on them. That's perfect. So you're slowing them down while you're speeding yourself up. And obviously that's beneficial if you're trying to keep up with the person. The rocket problem we'll let you guys handle in class. Hopefully these demonstrations help make it a little more clear how Newton's laws work. And if you guys have any questions, just send me an email.